Hello and welcome to another video on CHE 101. Today we'll be tackling the Henderson-Hasselbalch equation, which is one of the topics discussed in Physical Principles 2 or PHE 2. We begin with the theory. We start with the general setup of the Henderson-Hasselbalch equation. Then we go on next to a weak acid and its conjugate base. We discussed on how the Henderson-Hasselbalch equation for this form is derived, and we also discussed the Henderson-Hasselbalch form for a weak base and its conjugate acid. We will be using the Henderson-Hasselbalch equation and see how it relates to pH, pKa, and also with the concentrations of acid and its conjugate base. We will test ourselves with a problem statement. Then I'll provide the solution, and we will summarize it all at the end of the video. For a better understanding of the lesson we have today, you need some, it is recommended that you have some understanding on acids and bases and the pH scale and the K or the dissociation constant value. For the general setup of the Henderson-Hasselbalch equation, consider this case of this reversible reaction. The acid HA plus the base reacts reversibly to form the products, the cation HB, which is the conjugate acid, and the anion A, which is the conjugate base. Notice here that in the Bronsted-Lowry definition, the HA, the acid, gives up a proton to form its conjugate base. The base B receives the proton given off by the acid to form its conjugate acid. In here, the proton that I'm talking about in the Bronsted-Lowry model corresponds to the H, to the hydrogen atom. For this Henderson-Hasselbalch derivation, we shall consider the use of the dissociation constant, K. The dissociation constant is equal to the concentrations of the product side. So we multiply the concentration of the conjugate acid and the conjugate base, and we divide it by the reactants. So that's the concentration of the acid times the concentration of the base. For this, we shall be using the negative logarithm. What is useful here is that if we use the negative logarithm of K, we can use the pK value. Moreover, if we use the negative log for these terms in here, we shall be using the definition of pH and pOH later on. So this is the working equation that we'll be using to form the different forms of the Henderson-Hasselbalch equation. For a weak acid and its conjugate base, consider the acid HA in water, H2O, reacting reversibly to form the products, the HB, the cation HB. In here, it's the hydronium ion, H3O, plus the conjugate base. By the Bronsted-Lowry definition, the water here accepts the given off proton from the acid. So in this case, it makes a water the Bronsted-Lowry base for this reaction. And moreover, the hydronium ion, H3O, is the conjugate acid. We form the dissociation constant, hydronium times the conjugate base divided by the acid and the concentration of water. We use the negative log and we get this form. The pKa is equals to the negative log of the hydronium minus the log of the conjugate base plus the log of the acid and the log of the water. The pKa value Notice here that the negative log of H3O is also the negative log of the proton or the hydrogen. And notice that the negative log of this concentration of the hydronium or the hydrogen proton is equals to the pH. Moreover, since the concentration of water in this case remains constant and it doesn't change significantly in the system, we can take it off the equation. We simplify the terms. We put the pH on the left-hand side, the pKa on the other side, alongside the log values. We combine the logarithmic terms and we get this form. pH is equals to the pKa plus the logarithm of the conjugate base divided by the acid. This is the first form of the Henderson-Hasselbalch equation for a weak acid and its conjugate base. So if we know the concentration of the conjugate base, we know the concentration of the acid, and we know the pKa value or the Ka value, we can get the pH. And if we know the pH, we can also get the concentration of hydronium or the proton hydrogen in the solution. In this case, for a weak base and its conjugate acid, H2O reacts with the base B reversibly to form the products, the conjugate acid HB plus the hydroxide OH. By the Bronsted-Lowry definition, HA, the water here, uh, gives up a proton. It gives up a proton to the base B. In turn, to form its conjugate base, the hydroxide. And moreover, the base accepts the given off proton. We use the dissociation constant definition. Since we're dealing with base, we must know the dissociation constant of the base, Kb. Similar to what we did for the weak acid, we get the negative log and we simplify the terms. We define negative log Kb as pKb. We'll get that pKb is equals to the negative log of the conjugate acid minus the log of the hydroxide plus the log of the water plus the log of the base concentration. Again, since the concentration of water doesn't change significantly in the solution, we take it off the equation. Moreover, the negative log of the hydroxide is equal to the POH. Again, we transform this equation. We put POH on one side and the pKb and the log terms on we collectively put them on the other side. We get this form of the Henderson-Hasselbalch equation. The POH is equals to pKb plus the logarithm of the conjugate acid divided by the base. This is the Henderson-Hasselbalch equation for a weak base and its conjugate acid. So if we know the value of the Kb or the pKb, and we know the concentration of the conjugate acid and the base, we can solve for the POH. Moreover, if we know the POH, we can solve for the concentration of the hydroxide in the solution. So, what can we observe from the Henderson-Hasselbalch equation? pH is equals to the pKa plus the log of the concentration of the conjugate base divided by the acid. Notice, if the conjugate base is greater than the acid component, then the log term here will be positive. Then in this case, the pH value, the resulting pH value, will be greater than the pKa value. If the conjugate base is less than that of the acid concentration, then the log term will be negative. As a result, the pH is less than the pKa value. If both concentrations are the same of the conjugate base and the acid, if they're the same, the log will be equal to 0. As a result, the pH will be equal to Ka. Now, if we consider this case where the conjugate base is equals to 10 raised to n times the concentration of the acid, then it follows that if we simplify the log equation, it will be equal to n. Then the pH is equals to the pKa plus n. N is the exponent of the 10, the multiplier 10 here. So what this means is that if we have uh, the concentration of the acid and we know that it's 10 raised to let's say 1, 10 raised to 1 times greater, uh, uh, I mean, and the concentration of the acid is 10 raised to 1, and that's the concentration of the conjugate base. We'll know that the pH value is equals to pKa plus 1, since there's a tenfold increase in here. Moreover, if we put this 10n on the other side, then that means that there will be an n decrease in the pKa value relative to the pH. This is to make use of the log term here. And notice if we vary the concentration of the acid and the resulting conjugate base, we'll see that it has an effect on the pH value relative to the pKa value. So this is the summary of the Henderson-Hasselbalch equation. Given the weak acid and its conjugate base, and given the base given its and its resulting conjugate acid, these are the forms of the Henderson-Hasselbalch equation. Notice that pH is equals to pKa plus the log of the conjugate base divided by the acid. The pOH is equals to the pKb plus the log of the conjugate acid divided by the base. And these are the two forms to take note of for the Henderson-Hasselbalch equation. Let's put ourselves into the test. So I'll give you a problem and you'll try to solve it on your own. So the problem is as follows. Michaela wishes to prepare a 2 liter of a 1 molar sodium phosphate buffer, which maintains a pH of 8. Her colleague, Jonathan, prepared stock solutions of a 1 molar sodium dihydrogen phosphate and 1 molar of disodium hydrogen phosphate solution. So the question is, how much of each stock should be combined to obtain the desired buffer? We're given that the Ka is equals to 1.514 times 10 raised to negative 7. So we're given this resulting equation. The dihydrogen phosphate in water reacts reversibly to form hydronium and the hydrogen phosphate. So notice here that the dihydrogen phosphate gives off a proton to form its conjugate base, and the water receives the proton to form hydronium. So we'll be using this form of the Henderson-Hasselbalch equation. pH is equals to pKa plus the log of the concentration of the hydrogen phosphate, which is the conjugate base, divided by the dihydrogen phosphate, which is the acid. We have the pH is equals to 8, the Ka is equals to this value, and we have a 2 liter of a 1 molar buffer solution. We're given the stocks of the solutions. For the disodium hydrogen phosphate, it's 1 molar, and the sodium dihydrogen phosphate, we also have 1 molar. So we're required to find the volume of each stock solution. So pause and try it on your own and come back so that you can see the problem solving process and compare your answers. Okay, welcome back. Let's solve it one by one. So here I use the Henderson-Hasselbalch equation. We're given that pH is equals to 8. And since we're given the Ka value, we use the definition of the pKa. The pKa is equals to the negative log of the Ka value. We can solve for the logarithmic term, and the logarithmic term is equals to 1.18. Solving for the concentration ratio, we'll get that it's equals to 15.1356. So simplifying, the concentration of the um, hydrogen phosphate uh, is equals to 15.1356 times the concentration of the dihydrogen phosphate solution. So what does this mean? To make a 1 molar sodium phosphate buffer, we need 15.14 parts of a 1 molar disodium hydrogen phosphate with 1 part of 1 molar sodium dihydrogen phosphate. In total, 15.14 parts of disodium hydrogen phosphate using the 1 part of sodium dihydrogen phosphate totals to 16.14 parts of the solution. For 1 molar of the disodium hydrogen phosphate, we need 15.14 divided by 16.14, which is the total times 2 liters of the required buffer solution. So we need 2 liters of the buffer. We'll get that we require a 1.8761 liters of the disodium hydrogen phosphate solution. Moreover, for creating the buffer, the 2 liter buffer solution, we will need 1 part is to the total parts. We'll get that we require 0.1239 liters of a 1 molar sodium dihydrogen phosphate solution. So the complete solution in this case is that for a solution containing 1.8761 liters of a 1 molar disodium hydrogen phosphate, and we need 0.1239 liters of a 1 molar sodium dihydrogen phosphate to make a 2 liter of a 1 molar sodium phosphate buffer, which maintains a pH of 8. Quite a wordy statement there, considering that I'm not saying the chemical formula. So to summarize our video, the Henderson-Hasselbalch equation calculates the pH of a solution in which we know the concentration of the acid and the conjugate base, and we also know the Ka. We can also apply the Henderson-Hasselbalch equation for a base, where we can calculate the pH of a solution given the concentration of a base and the conjugate acid, and we also know the Kb value. If you have any questions, send us an email through chen.acads@gmail.com or reach us through Facebook, facebook.com/chen.acads. Thank you for watching and good luck on your homework.